Is it possible to demystify quantum entanglement? Well, at least partly demystify quantum entanglement. Is it possible to explain the mechanism behind the creation of quantum correlations? Well, the answer is yes. Stay tuned. Entanglement was theoretically discovered in the 30s of last century by Schrödinger and Einstein. But then we had to wait to the 60s of last century with the work of John Bell to really have a tool allowing us to test the presence of entanglement in physical systems, in experiments. This tool is the so-called Bell's inequalities. So the first step to really understand entanglement is to first acquire the tool of Bell's inequality. So we will start with that. Okay, let me briefly explain what Bell's inequality are about. I will not explain the original Bell's inequality, but a version of them called the Clauser-Horn-Shimony-Holt inequalities. These are the inequalities that are actually used in Bell test experiments. So what is the situation? The situation is that we have a system, a composite system, and in our case it will be a bipartite system formed by two parts. And these two parts are acted upon by two experimenters. One is named Alice, and the other one is traditionally named Bob. Okay, now Alice can select among two measurements she can execute. One is called measurement A and the other one measurement A prime. And these are two outcome measurements. They can just have two different outcomes. Same for Bob. Bob can freely select among two measurements B and B prime. Now Alice and Bob, they perform their measurement jointly, coincidentally. Therefore, they generate four different kinds of joint measurement. One joint measurement is AB, where Alice performs A and Bob performs B. The other one is AB prime, where Alice performs A and Bob performs B prime. Then of course A prime B and A prime B prime. Now let us assume that Alice and Bob, they denote the outcomes of their measurement by using the sign plus or minus. So they can have either a plus outcome or a minus outcome. This means that each one of these four experiments, they will have four different possible outcomes. They can have the outcomes plus plus, plus minus, minus plus, or minus minus. So here Alice has outcome plus and Bob also has outcome plus. Here Alice has outcome plus and Bob has outcome minus. Alice minus, Bob plus. And here both Alice and Bob have outcome minus. So we see here we have two outcomes that we can call them correlated because the sign is the same. And here we have two outcomes that are anti-correlated because the signs are opposite. Okay, so of course now Alice and Bob, they can prepare the system always in the same initial state, and then they can select which measurement to perform each time. They will do so, they will collect a lot of data, and these data will allow them to calculate experimental joint probabilities. More precisely, they will calculate the probability to have a plus-plus outcome for joint measurement AB, or a plus-minus outcome for the same joint measurement, a minus-plus outcome, or a minus-minus outcome. And of course, they will do the same for all these four joint measurements. So here as well. So they will collect all these joint probability. Okay, so we can collect an entire table of probabilities. I will not write them all here. Okay, so with all these probabilities for these four joint measurement, they will be able to calculate certain quantities which are the object of the CH-SH inequalities. So, okay, let's see how it works. Well, it's not very difficult. So, what we have to do, let's consider this measurement. Let's consider joint measurement AB. Now, to each one of these joint measurements, we want to associate what we will call a correlation function. Let us denote this correlation function EAB for this joint measurement. So, what this correlation function is meant to calculate? Well, we want somehow to quantify how much correlation there is in the system as opposed to anti-correlation, which means we want to quantify in a positive way correlation and in a negative way anti-correlation and see what is the trade-off between these two possibilities. So EAB is simply the following. We consider the probability for the plus outcome plus the probability for the minus outcome. So we could say that this is the probability for correlation, and then we want to subtract the probability for anti-correlation, which is the probability plus minus plus the probability minus plus. So you see, if we have perfectly correlated outcomes, this first term will be equal to 1, and this term with a negative sign will be equal to 0. So E will be equal to 1 if we have perfect correlation, and E will be equal to minus 1 if we have perfect anti-correlation. So, and of course, E will be, by construction, E will be in between these two value, perfect anti-correlation, perfect correlation, in between a trade-off between these two possibilities. So these are the quantities that we call correlation function. And of course, for each one of these 4 joint measurements, we can construct these correlation function. So we will have 4 correlation function that we can use. Now we will have just to combine this correlation function. I will tell you now how to do so, and this will allow us to state the CH-SH inequalities. Okay, so we have these 4 correlation functions. That we have calculated from the 4 different possible joint measurements. Now we will construct 4 different quantities. The first one I will call A, CH-SH, and this quantity is precisely the following. It is minus EAB plus EAB prime plus EA prime B plus EA prime B prime. This is the first quantity. Then I define, it's really a definition, I define a second quantity which is exactly the same, but here we have a plus sign and I put the minus sign here. Then only plus sign here. Then I define a third quantity where I have the plus sign here, a plus sign here, and now a minus sign here. So you see I put the minus sign in the different possible places, and of course here I will have a last quantity where I have plus, 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 and the final is a minus. Okay, so 4 different possible combinations where I always combine 3 plus and 1 minus. And now the theorem, the CHSH inequality is simply the statement that A or B or C or D, these four quantities, they have to be bounded between the values -2 and the values 2. So these are the inequalities to be obeyed. If these equalities are not obeyed, if they are violated, then we know that the system was prepared in a state, in a condition of entanglement. This is the theorem. And of course, to really explain why this is so, of course, we would have to really derive these inequalities under a certain number of suitable hypotheses. I will not do that because this will bring us too far with respect to the scope of this presentation. So here we have now the tool, and I will use this tool to study a very simple system. That's the next step. Okay, now I want to consider a very simple string model. A model where Alice and Bob operate on a very simple bipartite system. This system is simply a string, a white string, let's write here, it's a white string of length L. This is the system. And we can consider it a sort of composite system because the string has two different ends on which Alice and Bob can jointly operate. So they can perform measurement. Now let me explain what are the measurements they can perform. So what is measurement A? Well, measurement A is Alice that measures the length of the string. And how she does that? Well, she pulls the string and then she simply uses whatever instrument to measure its length. Now, if the length is strictly greater than L over 2, then the outcome is positive. If it's not, then the outcome is negative. So we have plus outcome if the collector string is longer than half the initial length of the string, or if it's not, then the outcome is minus. And of course, Bob is exactly the same thing on his side. Then we have measurement A prime. What is measurement A prime? Well, measurement A prime is about the color. Alice measures the color. And how she does that? Well, she simply looks at the string. If it's white, then the outcome is plus. And if not white, then the outcome is minus. And B prime for Bob is exactly the same, but on his side. So we have these two different measurements. One is a length measurement, the other is a color measurement. One of the two measurements requires to pull the string, the other one not. And Alice and Bob, they perform these measurements together. Now, what happens when they do so? Well, here we immediately see something. When Alice and Bob jointly pull the string, now what I have not told you yet is that the string is breakable. So if they jointly pull the string will break at some unpredictable point, which means that Alice and Bob will just collect a fragment of the initial string. And of course, depending on the point where the string breaks, either Alice will collect the longer fragment or Bob. So you immediately see that they will have anti-correlated outcomes. And of course, we can neglect the situation where they exactly collect the same length, because this is what mathematicians call zero measure event. Okay, So we see that when Alice performs A and Bob performs B, we have anti-correlation. On the other hand, when Alice performs A and Bob perform B prime, and we assume, of course, they jointly do the experiment in a way that Bob has enough time to see the color, of course, Alice will collect the entire string, hence she will have necessarily a positive outcome. And Bob will also have a positive outcome because the string is white, which means that the prime experiment, the prime measurement, they can only have here a plus outcome because, of course, the string will never be observed non-white. So in a certain sense, the measurement A prime and B prime are kind of trivial measurement with only one outcome. Okay, so this is the situation. Now, you immediately see we don't even need now to calculate the probabilities. We already know that the correlation function EAB will quantify a perfect anti-correlation. So this will be equal to -1. Whereas all the other joint measurement, I forgot the measurement also where Alice and Bob, of course, they both measure the color, of course, they also will get plus in this situation. So all the other joint measurement will have the same correlation function, and this correlation function will quantify a perfect correlation, so their value will be equal to 1. Now, at this point, it is easy to calculate these quantities that are involved in the CHSH inequality, Bell inequality. And let's consider the quantity we call CHSH, which, if you remember, it was minus AB plus AB prime plus B prime A prime B plus A prime B prime. Now you see here I have -1, here I have 1, here I have 1, here I have 1. So I have -1, this is 1, plus 1, plus 1, plus 1. Well, this is 4. And 4, no doubts about that, is strictly greater than 2. Hence, we have a violation of Bell CHSH inequality. Okay, before continuing, let me say that this string model is a variant of an ancient model that was invented by the Belgian physicist Diederik Aarts, and at the time it was called the vessels of water model. So this is exactly the same model, but now using a string, so it's a sort of simplified version. Okay, now are you surprised by this result or not? Well, maybe you are, maybe you are not. We have here a very simple physical situation which manifests a violation of Bell's inequality. For some physicists, this is quite strange because in the head of many of my colleagues, Bell's inequality, Clauser-Horn-Shimony-Holt inequality, they have to do with the micro world, with the atomic and subatomic world. And they are not used to think about these inequalities being violated in the macro world of ordinary objects. So this is possible. We can have this kind of violation. Now, what kind of insight can we gain from that? Well, why do we have a violation? Well, the reason for that lies in a difference between correlations of the first kind and correlation of the second kind, to use a terminology that was introduced long time ago by Diederik Aarts. So, correlation of the first kind are simply those correlations that were already actual before the execution of the joint measurement. Whereas correlation of the second kind, these are correlations that prior to the joint measurements are only potential. And these correlations are contextually actualized at each run of the joint measurement. And here you can really see that, because you see when Alice and Bob pull together the string, when they perform measurement AB, they jointly pull the string and they create a correlation which was non-existent prior to the measurement, because of course we don't know where the string will break. At each run of the measurement there will be fluctuations which are not possible to control, and these fluctuations explain the indeterminacy of the outcomes and also are at the origin of this correlation of the second kind, which are created at each run of a joint measurement. Now, is this the fundamental explanation behind the violation of Bell's CHSH inequalities? Well, the answer is yes, this is the correct way of thinking about these violations. And now let me show this in very simple terms. Let us consider the following. What would happen if instead of a whole string, Alice and Bob would operate on a string which is already broken? Imagine Alice and Bob have a friend called David. David likes to make pranks and he cuts the string before the execution of the measurement in some unpredictable point, of course, but the string is already broken in two parts. So what changes now if the string is already broken? Of course, when we consider measurement AB, nothing really changes. We will still have that AEAB is equal to -1. So the change is not at the level of the joint measurement AB, nor it is at the level of the joint measurement A prime B prime, because these are just about the color of the string. But there will be a difference for the two measurements A prime B and B prime A. Why? Well, because now when Alice pulls the string, she will not anymore systematically collect the full string of length L, which means that she will not always have a plus outcome, but she can also have a minus outcome. And same for Bob. When Bob pulls the string and Alice just performed the color measurement, he can only pull a fragment of it, which can be longer than L/2 or not. So we see that now we have a situation with these two correlation functions where we have the possibility of correlated outcomes, but also anti-correlated outcomes. And this means that this time these two correlation functions will be equal to 0. So here I will not have that. Here I will have 0. Here we'll have 0. And now I have minus 1 is 1 plus 1. Now I don't have 4, but I have 2. And 2 is not strictly greater than 2, hence I don't have anymore a violation. So you see that the fact that correlations are not anymore of the second kind, but they are now all of them of the first kind in the model, because the string is already broken, then this means that there is no more any violation.
Well, a nice little model indeed. I mean, it definitely violates the Bell CHSH inequalities. And yes, I have to admit, in the beginning I was thinking that an error was lurking in there somewhere, but the calculations are so simple and I could really check them. There's no error, so indeed it violates these inequalities. But it is also true that it does so with a magnitude of 4, which is the algebraically maximal possible value. And we know that in quantum mechanics we have a bound called the Chiralzon bound, which is 2 square root of 2, so 2.8 and something. And this is really smaller than 4. And so it seems to me that your beautiful little toy model, it has not a lot to do with quantum mechanics, precisely because it violates this inequality too strongly.
Okay, yes, I see. This is a valid objection. I imagine that one can be suspicious about a violation which is the maximum algebraic possible value. So let me see if I can slightly modify the model so as to have milder violations. Okay, so in order to address this objection, let me consider a slight variation of the previous model. We still have a string of length L, but now the difference will be that the string can also be blue in color. It can either be white or blue. You can think that the material is unstable, so it switches from blue to white from time to time, or you can think that the friend David, before the joint measurement, sometimes he replaces a white string with a blue one and vice versa. But let us consider that we know the probabilities of this fluctuation. Let us assume that PW is the probability for the string to be observed white, and PB the probability to be observed blue. Apart from that, we are exactly in the same situation as before. Alice always performed the color measurement A prime and the length measurement A, and Bob always performed as well these two measurements B and B prime. Okay, now of course when Alice and Bob jointly perform the AB joint measurement, they both pull on the string, they will break it, they will collect anti-correlations. So here, of course, the correlation function EAB will always be equal to -1. And also the fact that the string can change color doesn't change anything about the measurement A prime, B prime, because of course, even if the string can change color, Alice and Bob jointly only observe the same color. So this means that E, A prime, B prime will be equal to +1. Now, where there is a difference is, of course, in the two measurements A prime B or B prime A. Because now, when Alice pulls the string to measure its length, and Bob just observed the color, of course, Alice will collect the entire string. So she will always have a positive outcome, but Bob, of course, he can either have a plus or a minus outcome depending on the color. And here it is the same thing. So now we have a situation which is a little bit more complex, and it is very easy to check that in this case these two correlation functions now will be given by the probability to be white minus the probability to be blue. So now if we calculate the quantity ACHSH, we know that it is minus EAB, so this now is -1, so it is 1. Then we have these two quantities, and these two quantities now are twice P white minus P blue, and the last term, of course, is A prime B prime, and this is, of course, 1. So we have 1 plus 1 is 2, plus 2 P white minus P black, not black, blue. And P blue, of course, is 1 minus P white. So here we have, of course, minus 1 plus 2 P white. So this gives 2 minus 2 plus 4 P white. So we find that this quantity is equal to 4 p white. And of course, if the probability to be white is 1, then we are back to the previous example. But this probability now, it can be anything from 0 to 1. So we really see that we can have all sorts of situations. We can violate Bell's inequality, the CH-SH version, with whatever magnitude. And for instance, if we take p white to be square root of 2 over 2, then the violations will be exactly equal to 2 square root of 2, which is so-called Searle zone bound, which is the maximum value in quantum mechanics. So I think we have now correctly addressed the objection. The model is complex enough to allow for violation of different order. Therefore, this is not the problem of this very simple model in terms of possibly explain quantum correlations.
Interesting. So the model is also able to violate the inequality in a milder way. That's good. I'm impressed. But I have bad news, because I just discovered that your model violates also the so-called no-signaling conditions. And these conditions are instead obeyed by quantum systems, because quantum systems, the joint measurement, are modelized by product measurement, and so this ensures the obedience to these no-signaling conditions. So I'm afraid your model does not describe the actual mechanism behind quantum correlations.
Okay, it is true that the model violates the so-called no-signaling condition or marginal laws. But is this a true limitation of the model? Can we again make it a little bit more complex in order to have a situation where we have both a violation of the CH-SH inequalities and no violation of the no-signaling conditions or marginal laws? Well, this is possible, and this will be the next step. Okay, so now I have to address the issue that the model does not obey the marginal laws, the so-called no-signaling conditions. And of course, this is a strong objection, because in quantum mechanics, we have an obedience to these marginal laws or no-signaling condition. Well, at least this is what it is believed. In experiments, the situation is much less clear, because apparently these no-signaling conditions are constantly violated in experiments, but we think this is mostly due to error in experimental error, so this is not fundamental violations. Is it really so? Well, that's something that needs to be clarified. But okay, let's for the moment remain with our issue here. We have a model violating these marginal laws, and the objection is we need at least a model which obeys them to think that this model can somehow explain the origin of the quantum correlation. So okay, let me do so by slightly now changing again the model. But before doing so, let me first see with you what it means exactly to violate these marginal laws. Otherwise, we don't understand each other. So let me be back for a moment to the previous model so let me give you what are the different joint probabilities, which I didn't describe before explicitly. So let me write here P++ for the correlation, P plus minus, P minus plus, and P minus minus. And now here I have the four possible measurements, AB, AB prime, A prime B, and A prime B prime. Okay, these are all the situations. So now let me construct a table here. That's not difficult. This is the table. So we will have all the possible values. Now, of course, here we will have 1/2 and 1/2, because of course there is equal probability for Alice and Bob to get the longer fragments. The string is here assumed to be homogeneous. And then here we have P white, then we have P black, P blue, pardon, 0, 0. Then we have P white, 0, P blue, 0, P white, 0, 0, P blue. And I leave it to you to check that these are exactly the joint probability of the problem we have previously considered. Now you immediately see here that if I want to calculate the probability for Alice when she performs measurement A to have a positive outcome, irrespective of the outcome of Bob, then if Bob is jointly performing measurement B, when what it will be this probability, then it is the probability having plus, so it's that probability plus that probability, with Bob, who can have either plus or minus. So I have to sum this probability with that one, so it is 0 plus 1/2, and this is 1/2. But I could also consider the situation of Alice having a positive outcome while measuring A, with Bob executing measurement B prime. And in this case, of course, I am on this line, and then, of course, the probability are these two. So it's P white plus P blue, and this, of course, is equal to 1. And 1 is different from 1/2. So these marginal probabilities are different, which means that Alice has somehow the possibility, by analyzing her probability, to understand what kind of measurements Bob is jointly performing. Okay, so this is the violation. Now I need to show that it is possible to consider a model where there is no such violation. So how can I do that? Well, a possibility is to consider exactly the same situation, but this time I will define measurement A and B in a different way. Now A and B will be, let's consider the situation for Alice. For Bob it will be exactly the same thing. Now Alice, when she performs measurement A, she will still pull the string and measure its length, but she will also measure its color. And she will consider the correlation between length and color. And so she will consider that if it's long and white, or short and black, this corresponds to outcome plus, or. So long white, short black. She will jointly consider these two properties and the correlation. And of course, if it will be short white or long black, it will be, otherwise it will be the outcome minus. And Bob will do the same when performing B. So this changes the experimental situation, of course. I've just changed the measurement that Alice and Bob perform on their subsystems. Okay, now one can think about what changes in terms of the probability, the joint probability. So I leave it to you to go into the details of a model. Otherwise, it will become a little bit boring if I do all this here on the blackboard. But what is important to see, this you have to believe me somehow, is that with this new definition of the A and B measurement, then the probabilities here will change, and we will now have here 0, 0. Here we'll have P blue, and P blue. So we will have this different table now. And now you see with this different table, you see that what happens is that, of course, for this marginal, it will be the same thing, 1/2. But for this marginal now, I have this plus 0. So instead of that, I have this plus 0, and this is P white. And now, of course, if P white is exactly equal 1/2, which is a choice I can make, then my model perfectly obeys the marginal laws. In this situation, one can check that all the other marginal laws are obeyed as well. But now this model, of course, violates the Bell-CHSH inequalities, because we have perfect anti-correlation for this measurement and perfect correlation for the others, which means that the quantity A is exactly equal to 4. So we have again a maximal violation of the Bell inequality and a perfect obedience of the marginal laws. And this, of course, I think addresses the objection.
Okay, congratulations. So you managed to have violations of Bell's CHSH inequality and obedience to the no signaling conditions. Good. But the violation now is back to the 4 value. It's again a fixed value of 4, the maximum value. So it seems to me that if you try to fix one part of your model, then another part of it has a problem. I'm afraid that this model is nice, but not the real deal.
Okay, so now I have to address this, I hope, last objection. And this last objection is, yes, about the fact that what I have shown you previously is a situation where indeed you have obedience of the marginal laws of the no signaling conditions and a violation which is algebraically maximal. And now the objection is, well, yes, but again, this is kind of pathological to have this maximal violation, which is not obtainable in quantum mechanics. So let me show a situation where we can have not only the non-violation of the marginal laws, but also the possibility of having different degrees of violations of Bell-CHSH inequalities. All right, so one has to think again how to complexify a little further the model to have it rich enough to also be able to describe such a situation. Now, what I'm going to do is I'm going to keep the measurement of Alice and Bob exactly as they were. So the primed measurement are just about color, and the A and B measurement are about the correlation between length and color. But it's not enough, so I will now consider the system as being made now by 2 string instead of 1. 2 string, which can be white or blue, with these probabilities, of course, which are the same for the 2 strings. Of course, I could consider different probabilities for the 2 string, but it becomes too complicated. And so I have 2 string now, and so Alice, when they pull, they might pull one or the other, so the system is a bit more complex. And let's say that they will pull this string with probability P1 and this one with probability P2. Let's say that these probability P1 and P2 are the same again for Alice and Bob, because there is no need to make the model too complicated. Okay, so I have now not only these P white and P blue probabilities, I have also the probability of pulling string number 1 or string number 2. And of course, this will introduce much more structure in the model, because now, as you can imagine, there is the possibility for Alice and Bob to jointly pull a long string. I mean, the entire string. It's sufficient that they pull a different string. And they now can also have different colors, because, of course, again, if they pull a different string, the color need not anymore to be perfectly correlated. So you see, you have a much richer combination of possibilities. Now, of course, I could try with you to go into all the details, but now the calculation become a little bit more involved. They are not difficult, but you really have to be careful to take into account all these possibilities. So now you have really to trust me, otherwise again the video will become just boring. So I have done properly all the calculation, and now the result of this calculation is that the correlation function EAB is minus 1 plus 4 P1 P2, and here in the parentheses I have 1 minus 2 P white P blue. This is the expression. And for the other correlation function, they are all the same, and they are given by 1 minus 8 P1 P2 P white P blue. So this is the result. Now, of course, now you can put this inside the quantity ACHSH and look what you obtained. Now, before doing that, one also has to now check what happens for the marginal law. So I will not do all this because it becomes a huge calculation, but what I can tell you is, and trust me, please, is that when you set again P white equal P blue equal 1/2, then again, as before, the model perfectly obeys all the marginal laws. So from that viewpoint, we are safe. But now, if we have this, we can also show that in this circumstance, then this A quantity, which is in Bell's inequality, is equal for P1 square plus P2 square. And this you see immediately that this, of course, it can be equal to 4 if, let's say, P1 equals 1 or P1 equals 0, of course, then you will have a maximal violation, but we can also have different degrees of violation, of course. If, for instance, we have P1 equal P2 equal 1/2, then P1 square plus P2 square will be 1/4 plus 1/4, which is 1/2. And then you see that in this case here, if P1 equal 1/2, then we will have 4 divided by 2, which is 2. So we have no violation in this situation. So we can go from the minimum violation to the maximal one with no problem. So again, the model has enough richness. And of course, in between, you can also reach the 2 square 2 value, which is the maximal value for quantum mechanics. So I have shown now that the model, with all these variation, can reach the stage of being able to obey or not obey the marginal laws, and to violate or not violate Bell's inequality. So we have all this freedom. And so the mechanism which is behind these violations is general enough, and it's probably, I would say, the mechanism which is also behind the violation in quantum experiments, which is the fact that we have some hidden interactions when the measuring system interacts with the measured system. We have interactions which are potential, as all these breaking points are potential, and these are actualized every time. So this model provides a lot of insight into what is a possible mechanism in force, also when we perform experiments on entangled microscopic entities.
Well, I'm impressed. You succeeded to respond to all my criticism. Very good. Bravo, bravo. But I am still not believing that the mechanism that your model makes explicit would be the mechanism in force in atomic and subatomic systems. Because you see, if this would be true, I think that these hidden interactions which would be responsible for these correlation of the second kind, as you call them, this should appear somewhere in the quantum formalism, which I think is not the case.
Okay, yes, thanks for this last criticism. Yes, I understand that one would like to have within the quantum formalism a hint about the possible existence of these hidden interactions that would explain how these correlations are each time created when we execute the joint measurement, the equivalent of this breaking point of a string. Now, the good news is that, in fact, there is a way to represent the states in quantum mechanics, and not only the states, but also the measurement, which precisely suggests the existence of these hidden measurement interaction, potential non-local interaction between the measured system and the measuring apparatus. So this representation is called the extended block representation of quantum mechanics. It happens inside the so-called block spheres, a generalization, of course, of the block sphere, because when you have measurement having more than two outcomes, the block spheres is not only three-dimensional, but it can become n square minus one dimensional, so everything becomes much more complicated, of course, but you still have very nice structures inside, inscribed in the block spheres, which are simplexes, which represent this potentiality region, which is at the origin of the creation of correlation, of the collapses, and so on. So actually, there is within the quantum formalism the indication that what is also suggested by this model would be in force also at the microscopic level. Of course, nobody up to now has ever directly observed the existence of these hidden interaction, and let's hope that in future experiments we'll be able to do so.
Okay, so there is, after all, an indication in the quantum formalism that these hidden measurement interactions responsible for this creation of correlations might exist, even though remaining still at the sub-empirical level for us. But yes, let's hope we will be able one day to have evidence of their existence. And I think that if this will be true, some Nobel Prizes will come, indeed. But let me express a last point of criticism. When you have two entangled electrons or photons or whatever which are flying away and they are separated by very large spatial distances, what would be in this case this connective element which would play the role of the body of the string, so to say? Because you can find nothing in between them. And this, in my view, is a very strong counter-argument for your model. What do you think?
So yes, this is where quantum entanglement becomes really mysterious, of course, and really different from the situation of macroscopic object-like system like our string. Of course, the string which Alice and Bob experiment on is a whole entity. You can consider it as the joining of potential fragments, which can be of different lengths, of course. And these strings, of course, they are kind of interconnected through the very body of the string. So Alice and Bob, they can operate it at the two ends, and the string itself plays the role of a connective element. But now when you have, say, two electrons with their spins flying away, very far away in space, you cannot find anything within them in space. So there's nothing in space which you can think about, which would play the role of an interconnective medium explaining the creation of the correlations. But it would be wrong to think of these quantum entities as entities that would be representable entirely within our space-time theater. And these connections within the extended block formalists, they can represent it, formalize, and we see that they have a dimensionality which is much higher with respect to the dimensionality of the individual state of the subsystem. So there is reasons to believe that these interconnections exist, making the entangled system as a whole, but they are not manifest, not available to be detected using three-dimensional measuring system. And here, of course, we touch the true mystery of quantum mechanics, which tells us somehow that our reality is not fully contained within our spatio-temporal theater, which is too small to represent all the typologies of entities that exist out there and their possible interaction. Thank you for listening.
Okay, hello and thanks for all these very nice explanations.